All right, hi everyone. Welcome to the Unreasonable Effectiveness of Monads. Before we get started, I'm just curious, has anyone here before worked with, or at least played with Haskell? Just raise your hands. Okay, big chunk of the room. You may not learn as much in this session because if you've ever had to use that language, you've probably already interacted with these concepts. Also, again, just absolutely curious, who's working with Haskell professionally? One, yes. Excellent. Okay. So this is one of my favorite Dijkstra quotes. There's two of these in this talk. Simplicity is the prerequisite for reliability. Simplicity doesn't mean familiar. It means things that are actually made of few parts. A little bit about me. My name is Zelenka. I'm XP'd all over the internet. I am the co-founder and CTO at a company called Fission, where we're inventing what comes after serverless, which is the next talk I'm giving this afternoon. I'm a programming language theorist and virtual machine enthusiast. I'm obviously very into functional programming. I wrote a bunch of libraries in Elixir that port essentially the Haskell standard library to that language. And I used to teach Elixir professionally as part of a consultancy. It was one of the services we offered. But now Fission is a Haskell shop for the back end. Sales pitch for this talk. Basically, there is a broad trend towards functional techniques in general. When I started my career, I had to literally explain to people what a mapping function was. Down to, it's like a for loop, but really specific. Now it's built into every language. Everybody knows how it works. It's just assumed knowledge. A lot of people don't even think of it as being a functional technique. It's just something that they have available. This also lets us handle increasing complexity. I'll be talking a little bit briefly later about structured abstraction. But it gives us an easier way of thinking about more complex things as we're doing more networking and just more moving pieces. As I mentioned just a moment ago, familiar does not equal simple. So sometimes having a investment in understanding a simple thing actually makes it easier to work with than the things that you've already been trained to do. And you're sitting in the polyglot and fringe track, so I hope you're ready for some polyglot stuff. So this is the maybe boilerplate level or the burden to getting started in a language. So you see, you have totally unconstrained. You can get running just immediately, and then you have these structured abstractions that take a little bit more. If you ever worked with, say, Elm or Redux, you know that there's more boilerplate, there's more setup at the beginning, but over time, it levels out, and if you're not using any of these structures, complexity can explode. So back in the, I guess, late 70s, early 80s, people were still using gotos all over their code. There's a famous paper, gotos considered harmful, where it's argued that by adding just a little bit of structure, switching to loops, we lose a bit of the familiarity from what people were using at the time, but we get a lot better growth in the code. The complexity is more controllable. Monads are many things. Today we're going to be focusing primarily on effects. Monads are extremely well defined, literally mathematically, so we're going to steer straight away from the math. Again, many uses and many different ways of looking at them, but the one practical thing that you do with them in day-to-day work is handling of effects. So very, very broadly, we're going to start with some concepts that you already know about, talk in sort of high level about abstraction, give you probably the most unfamiliar part of the talk will be these technical prerequisites. Then we'll run through the essence of the monadic style and then give some examples at the end. And all of the examples will be given in Haskell, Elixir, and JavaScript. So I've already used this term a few times already, structured abstraction. A structure, obviously, is a mode of building, organizing, or constructing something. For example, a pyramidal structure. And abstraction is getting down to the essence of what a thing is. So taking many different things and saying what makes them common. When you have more generality, you can say you've taken that abstraction to a high degree. So you can say, for example, with a mapping function, that it works in a very simple way on a bunch of different kinds of structures. So you have an array or a tree or any of these different things, and you can map over them in this way. But we don't necessarily know a whole lot about it. And the more specific information you have, the fewer things it's going to work on, and the more specific to a particular use case. So FUNCTOR or enums, which are things that can be mapped over on one end, and then say a database or a SQL library on the far other side. And right in the middle here, we have Monads, which puts it in a really nice point in the design space. To give a very simple example of a structured abstraction, we can talk about semigroups. So it's not a data structure, it's not a function, it is an interface and some rules that go along with it. So it's the essence of anything that that's associative, right? So I can take A and B and then C, or A and then B and C, or if you prefer more of a JavaScripty notation at the bottom here. So let's look at it. In Haskell and Elixir, we have ad hoc polymorphism, so we can say in advance, I will have some kind of interface that looks like this. JavaScript doesn't have that, so I skipped it for that part. So here it is on integers. We can do integer addition. You can also do integer multiplication, because these are associative operations. You can also do that on lists or arrays. So now you have the same interface for doing addition, multiplication, and array and string concatenation. They're all the same kind of thing. We need it to be associative because if we were to do this with division, we get different results based on where we place the brackets. So we use a lot of different features every day. Very common one is promises, which is already abstracting over a large number of things, right? We're saying we're going out into the world and doing something, or maybe it's a very long computation without going out over a network. And I'm going to get a result of that back later at some point, but don't worry about how that's being handled in the meantime. We have throw catch, tracing, and context or config values. So if you've used React, for example, they have this context idea where you can thread through sort of implicit variables through your application. So these are all different, but maybe there's something that underlies them that's similar. So try catch, you can do many things in this try block, and then it'll either continue outside, or as soon as something goes wrong, it'll pop into the catch. Then you have an opportunity to handle the error and then continue on. With logging or tracing, you are going along and you're saying inside each of these functions, I'm going to write out to my log. And then when I actually call it, it'll actually run that. And then, of course, promises, we do this sort of threading as things become available over time. Another way of writing that is like this, right? So you can, this is the more powerful form, even though it's less readable, right? So you can nest it in this way, and it has a data dependency in it, right? So these are all sequences of events. Some of them have data dependencies, some of them are waiting for things, and there's always this sort of an effect happening as we go through. Right? They're different effects, but they all have something in common. So the big takeaway here is you're already doing this, right? These are surprise attack effects. And we can clean this up with a single interface. So instead of side effects, let's talk about front effects. So a side effect is an implicit effect that happens off to the side. It's typically handled by your language directly. They are not inspectable in general. Sometimes they are, often they're not. If you want to look at the log, you have to go and actually go over to the log and take a look at it. Yes, and they're obviously difficult to test. You have to set up this whole testing framework around them. Effects as data. So we can model effects purely as data. So you have some carrier data that's going to do all the bookkeeping you need as you go along. Data is extremely simple. It's even simpler than functions. Right? It's literally the raw matter of what we work with. They don't need to be separate, right? So we can carry them along as we go. You can write your own. You don't have to rely on the language to implement a new feature. You can just write them yourself. You can inspect them as needed as you go along in your application, and you can compose them as well. So we won't be talking about how you can layer effects, but that's also something that's absolutely possible too. So the monad is a common interface to make all of those things straightforward. And the upshot is that you learn this pattern once, and then you can use it in many, many places. So let's look at the functor tower. This is the internals bit. And this is that second Dijkstra quote. Progress is only possible when we train ourselves to think about programs without thinking of them as pieces of executable code. So sometimes you want to take a little bit of a step back from your code to think about it in a more general way so that you can make some assumptions about how it'll behave. So functor, also known as something that's mappable, right? It always returns the same shape. So if you give it an array, you'll get back an array with the same number of elements. You give it a tree, not only will it be the same number of nodes, but they'll be in the same arrangement. So this is something with a mapping structure, and I'll keep the tower going in the side there as we go along. So in the Haskell version, give you both the abstract form and then an actual implementation of it. So this is on a list. You can map over it, an empty list, obviously. You get back an empty list. Otherwise, you map over each element and you go along. This is probably fairly familiar for most people. Same in Elixir and JavaScript. The main thing to note is that there's some rules that go along with it, and these are the only rules that I'm going to give in the slide just to keep space. But all it says is that if you map over some structure twice with two functions, it's the same thing as, so you take the whole thing, apply the change to it, and then apply a different change to it. It's the same as taking it and applying those two functions to each element in turn. Right? So we can do this back and forth. And if you map the identity function, you get back just the normal thing. So if it doesn't respect those things, you will have edge cases that behave in a weird way. Next up is apply. So this adds the ability to take some regular data and wrap it in a container that's going to do all the bookkeeping for us. Right? So you can think of this as the new keyword in JavaScript. And sorry if you already know Haskell, I'm going to be butchering the language a little bit to make it, oh, sorry, that's applicative, apply. We take something that's already wrapped, and you take some function or functions that are also wrapped, and you apply all of the functions to all of the data. And they have to be in the same kind of container. So on a list, you'll take a bunch of data and a number of different functions and run all of the functions over all the values and get back a single list, not nested, with all those values in it. For something that's tracking whether or not something has failed, if you run some function elsewhere that then returns, say it's a higher order function, and it says only run this under these conditions, it can return back an empty container, and then nothing will actually get run because you have no function to run it on. And it can handle all that effect for you. There is one problem on this slide. In the JavaScript implementation, this push should actually be a concat. As it's written, it'll give you a nested arrays. Applicative is the one that I was talking about a second ago. So this one takes some regular data and wraps it in a structure for you. So I have just a number, say 42, and I just want to wrap it in an array. This is, in Haskell, normally called pure or return. I'm just keeping it consistent for now, because it's literally what it is. It just wraps a thing. So that's this branch in this tower. On the other side, so not needing that wrapping function, we have something called chain, which has a bind function on it. And what bind does is it takes something that's wrapped, pulls the value out of it, applies a function to it, and that will return that complete structure again, and then continue on. So where a apply, which takes wrapped data and wrapped functions and applies them together, but that only has a certain number of arguments, so you're done when you're out of arguments to fill. Chain, you can keep chaining forever. This is also known as flat map in a lot of languages, which is a very sort of, I guess, operational way of thinking about it, because you can always implement it as mapping and then flattening the structure, though it's not always the most efficient. And then when you have something that is both wrappable and bindable, you have a monad. With the powers combined, you get a monad. Monads are the essence of a Turing-complete, possibly effectful computation. So you don't have to have effects. You can have effects, but they can depend on previous points in the chain. So this is the absolute essence of something that can continue forever. These things aren't related together by accident. They're in a hierarchy for a reason. So when you have a regular function call, there's no effect being moved across, right? Here's regular data, regular function, you get a regular result. With a FUNCTOR, which has a mapping function, you take some wrapped data, take a regular function, and apply it to all the elements inside, and get back wrapped results. With apply, you take some wrapped data and wrapped functions, apply them together, and get wrapped results. And chain, wrapped data, and this linking function that goes from something that's unwrapped, because we're going to pull it out of that structure, and then wrap it again. And that's what lets us do that forever linking. So finally, we have the the components of what makes up a monad. So let's look at some actual examples. Either or result, depending on where your language background is coming from. This is used for railroad programming. So this is the try-catch from before, but with some extra steps in it. And looks like this. So we have three tracks. We have a happy path, which is as if everything had continued normally. We have our error case, so our throw, which will skip. And we have no effect, which is everything outside of this block. So happy path, we try our possibly exploding function, and if it does go wrong, then we pop down into this error case. Next, as we go along, we try the next function, and again, if there's an error, we drop down to the second track. If you're already on the second track, don't do anything, just keep moving. And we can do this again, and again. And then when we get to the end, we have the ability to inspect it and possibly handle the error or do something else with it, which is just like the catch block. So each of these points where it can possibly skip down to the next level is the bind operator or function. So we need some carrier data to track which effect, how the effect works. So we're going to call this results, and it can be one of two things. It can be an OK or an error. In Elixir, we fake this a little bit by using types in an outer module. In Elixir, you can actually lie to the type system, so it's not perfect, but it gets you most of the way there. And in JavaScript, we could have inherited from a result class, but it doesn't actually really get us anything. So we just have these two, and we'll have to do the tracking that these are the same kind of thing in our heads. In TypeScript, you can do this, but not in raw JavaScript. So let's look at a couple instances here. So these all do the same thing. The functor, so to do a mapping over this, if you have an OK, then actually go inside that wrapper, apply the function, and continue on. Otherwise, if you have the error side, don't even bother doing anything with the function. Just return the whole thing and keep going. For applicative, which is the wrapping, so I'm not going to do the whole tower for each of these, just the parts that we're looking for to do this chaining effect. Right? For an applicative, we want to take some bare data and wrap it in the correct structure that we're going to be using. So in this case, we'll stick it in an OK. And same goes for even in the error class here. We're going to wrap it in an OK here as well. So both the OK and error in the JavaScript implementation need to return the OK side. And then same thing for the Elixir version. Does the exact same thing. Now, how do we use this? The simplest way is to, so you can use it with anonymous functions. But if you name functions, you can get this completely automated for you, and you don't even have to think about it at all, right? So we have this even or error function. It will try to find if something's even. If it is, it will wrap that value. And if it's not, then it will return the error side. So in the Haskell case, we give it a specific data type to tell you how it went wrong, called not even. In Elixir, we can do this just with a tuple and an atom. And in JavaScript, we just give a string. You could make it a class if you really wanted to, but you don't really get as much benefit in that language. Haskell, again, for the people who've seen it before, we do have some nicer notations, and it's a very expressive language, so we have a few ways of writing it, but that doesn't really translate over to these two, though we do have do notation in Elixir with a macro, which is nice. And then we can take this, so that weird symbol in the Haskell version, this double arrow equals, which is also where Haskell gets its logo from, is the bind function. But even this looks a whole lot like .then in promises in JavaScript, right? We just say .bind, and here's my function, here's another function, here's another function. We can keep doing that forever. Let's look at writers. So this is logging. And we can do the actual logs themselves in a couple different ways. You could do logging in the traditional sense. So you have something outside of this watching for logs and then writing them to some central logging place. The more interesting thing is doing this in a distributed system where, because your log is attached to your data, as you're sending it around, you can write into a log that's literally tied to your piece of data. So you don't actually care where it's being computed, just that it's being computed, and you can keep the log for that entire movement. So in this case, we have two tracks. We have the actual program, and then a log that we're going to be writing into, right? So we're going to be pushing the effects up into there. So carrier data on this one. It's actually very simple. We have, so in the Haskell case, just an outside container for a tuple, for the value and the log. In Elixir, exactly the same thing, but in a struct. And in JavaScript, we just use 2 values to do this. The actual instances. So it's a little bit more involved at for the instances, because now we need a few things. The logs need to be able to append with each other somehow. So we have an extra constraint here. So in the Haskell version, it's explicit. We have a monoid, which is a semi-group with an empty element available, right? When we map, we only map over the value portion, not the log. And we can go in and, when we run 2 of these together with a bind, we run the computation, get back both the result and the log, and then append the log to the old log so that we continue that going along, which is basically this line here. So we actually run the function on the old one and then concatenate those together. And then same thing in JavaScript and Elixir. Now, how does this look when you use it? Again, it's often helpful to have named functions for this. And we also have some helper functions as well that are just kind of written off to the side. So you have tell, for example, which will return no value and some log, so that when we run this with something else, we just get the logging part and we're throwing away the old value, right? We have a function called half, so we're going to half some value as we go along and write into the log. Number divided by 2 equals, and then the result. And when we actually go and run that, at the end of this whole thing, we have a list or an array of each step that we took. And again, it doesn't matter where this was run. We could even take the entire structure, save it to a database, pull it out again a year later, and keep running it. And we'll have the entire log attached to that, which is very, actually surprisingly handy. And finally, we have the reader, which is for config or context injection. And it sounds like a really simple thing, but gets used actually quite a lot, because this is a way of doing scoped variables. So you can do global variables for your entire application in a totally functional way that is even parallelizable, right? So again, we have these 2 tracks. We've got the effect being managed on this top track, and the bottom one, this black line, is the actual program. And we can go into it and grab this read-only data at any point, right? So again, this is like what in React you have this.context, just being threaded through your program. This is probably the most involved of the 3 that I'm going to be going through. So, and it's a little bit mind-bending if you're not used to it. So we have some function, which is and inside this wrapper, but that's our carrier data. Really is this function, right? It looks very bare in the JavaScript case. At least we have a little bit of suggestion of what's happening in Elixir. We have some instances. So when we map over this with a function, we create a new reader on the outside, create a new environment argument to wrap the old one, and then apply the function to the old function. So we have this threading of the environment happening, right, that we're going to pass in, which means that when we finish doing all of this, right, wrap, not much interesting there. With the bind, we do the same thing again, but it's like a flat map, right? So we get a reader inside a reader, and then pop the function out of it. The end result of this is you have now a chain of function composition going all the way back that doesn't change the values inside of it, but where you can map and change the result of that of the function inside. So when you pass in, my theme has these properties, that will always be passed through, and you can grab that back out as part of a bind. So the use of this then becomes deceptively simple compared to the setup, right? So we can just say, Elixir has pipes, which is kind of like dot syntax. We can say ask, which is give me the that environment or that config back out, because I'm just going to map into this the identity function. So I can grab that back out, count the number of things in my environment, even print it out, and while doing other computation inside of this, right? Obviously, same thing in Haskell, shows more the indentation in this notation. And in JavaScript as well. We can just keep doing .bind all the way through and get this automated behavior. The one extra piece you need to do at the end, so this is just doing function composition really, is you need to actually run it and pass it some environment to work with, right? So we have run my function, or my function.run, depending on which flavor you prefer. And then the context you're going to thread through, and you'll get back different results based on your environment. So that is Monads, which is a lot of power for a handful of functions. And that's all from me. Thank you.